So what I want to do in this video is give you just a series of 4 examples that's going to show you many different ways to apply the idea of CMBRs, CMFRs, so completely mixed batch reactors and completely mixed flow reactors with reactions. So in these types of problems, what you're going to have is you're going to have a tank or maybe some sort of class, like room, or some reactor that you can assume is well mixed. You're also going to have some sort of reaction. So this could be a generation reaction or a consumption reaction. If you have a situation where you have flow through your reactor, then you're going to be modeling it like a CMFR, so a completely mixed flow reactor. If you have a situation where there is no flow through your reactor, you are going to be modeling it like a CMBR, or a completely mixed batch reactor. In this particular video, I'm not going to talk about plug flow reactors or PFRs, but that is another option that you would use if your reactor was very long, like a pipe or a very long trough or tank, or a tank with baffles. So the first example that I want to do is a completely mixed batch reactor with first order decay. I'll do a sketch here of a batch reactor. It has no flows in or out. That's what a batch reactor is. But I do have some sort of reaction here, which is a decay. So my reaction term is going to be negative because the concentration of whatever I am looking at is going to be decreasing. I can write this out. The V is the volume of the reactor. C is the concentration within our reactor. And I don't have in or out terms, so I only have this first order decay where my reaction rate is Kc. And I can simplify it here. If I were looking at steady state for this particular system, I would set dC dt to 0, and then I would just find that my reaction, or my concentration, is 0. So at steady state, there's nothing left. If I wanted to figure out how C changes with time, I would just do an integration and solve for C as a function of time. In my second example, I want to show you a completely mixed flow reactor with second order growth. So if I were to draw some sort of tank, I have flow rate V dot coming in and out. I have some concentration C in entering my reactor, C is exiting, and my reaction rate within my reactor is Kc squared, which is second order growth. I'll write my mass balance equation here because I have growth. My reaction term is positive. V is the volume of the reactor. I'm looking at how the concentration within it changes with time. I've got my in and out terms, and then my reaction term is going to be plus Kc squared. If I wanted to solve for this system in steady state, I would just set dC dt to 0 and then solve for probably C. Or if I was interested in how C was changing with time, I would need to integrate this equation to solve for C as a function of time. Finally, if I wanted to not actually look at a CMFR, if I was looking at a CMBR, a batch reactor with second order growth, what I would do is I would eliminate those in and out terms and work with that. For my third example, what I want to do is show you how to set up a CMFR flow reactor with MONDO decay. So remember, this is a type of reaction kinetics that also depends on biomass concentration. Minnow decay is a little intimidating perhaps at first because the reaction rate is complicated. It includes X, which is the biomass concentration, and this term K1/2, which is the half specific growth rate for the microorganisms, in addition to our C term. But you'll see that we set it up the same way. And just be sure whenever you're doing, especially if you're doing kind of strange reaction rates, but also like just in general, always be sure that you're checking and double checking your units to make sure that the units of each one of your terms is exactly the same. In this example, it's going to be some sort of mass per unit time. If you're looking at steady state, set dc dt to 0 and solve. If you want to do a CMBR, you eliminate those in and out terms and solve for whatever you're looking for. My final example, I want to do some flow reactors in series with a first order decay. So you might see this. You might see several reactors in series, and you can actually solve a number of different types of problems with CMFRs in series. So in this particular example, I'm just going to do 2. We have to be really careful with how we designate our concentration. So remember, in CMFRs, the concentration coming out is the same as the concentration within the reactor. And what you want to do is do a mass balance around each reactor. So I'm going to call these just reactors 1 and 2. So for reactor 1, I'm going to be really careful. So this is going to be V1. So the volume of reactor 1 and the change in concentration in reactor 1, which happens to be C2, in minus out, and then we've got our first order decay term, so minus KC2 times the reactor volume. I can then do a very similar equation for reactor 2, where I solve for the change of reactor 2 concentration, which happens to be C3, the way I've designated it, and the equation looks quite similar. So hopefully that gives you a little bit of an idea about the types of problems that you might see that use both reaction kinetics and the idea of ideal reactors. Hopefully you saw some similarities in how you set it up using reaction rate constants and different types of assumptions you can make. Notably that if you're looking for steady state concentrations, you just set that accumulation term to 0. If you're looking at a batch rather than a flow reactor, you eliminate those in and out terms. And if you need to solve as a function of time, you are going to end up having to do some integration.